Okay, so in this short video, we are going to talk about the first classical regression model. Is called linear regression by the least square methods. Okay, so recall if you took any statistic class or the data science computing class, we already gave you the linear regression. That the function we choose is just the linear function. So the regression function is 1, and we plus the squared loss function. So we choose A, and also the cost function is the average square loss, so mean squared error loss. So in other words, we are looking for the problem is actually the optimization problem, that we are looking for the weight W, intercept alpha, that minimize the mean squared error loss. So 1 over n. So you go over each data point x, inner product with W plus alpha. So this will be your model. So this give you y hat, and the differences with observed y, and you take as a square. Yes, so that's the linear regression problem. So here is one example. Suppose we have a data set with 2 independent variable x1, x2, and the responsible variable is y here. And we have the 3D scatter plot. Okay, and the question is, how can we find the best fitting plane that minimize the distance between each observed y and the predicted y. Predicted y means the prediction by the model, so it's y hat here. Yi here. Okay. Okay, to solve the formulas for the W and alpha, we need some matrix notation. So here X is our data set, is denoted by the N by D. This is usually in statistics is called the design matrix of sample points. And the Y, we have the univariate scalar labels. Okay, for example, your data is usually summarized. For example, in the Excel file, you have different columns, right? You have the first variable, second variable. Suppose we have the D variables, right? D features, and the row index denotes a sample. So So I equals to 1. So our first observation is the first row. I equals to second row, second observation. And I equals to n is last observation. And we have the first observation was the first feature, okay? First observation, second feature. And the first observation, the last feature. And we can, so for each individual I, we have this. So basically for the ith row, we have the I1, xi2, xid. Last, it will be the xn1, xn2, xnd. Okay, so this is our design matrix X, and each row we have a notation, so it's a data point. Sample point xi transpose, because usually we denote the a column vector, vector by column vector. So each row here represents a data point, Also the y, we have the y, right? So for each observation, maybe let me write down as the same row. So our y. So for each observation, we also have the labels y1, y2, yi, yn. Okay, so this is our response variable vector. Usually we have our sample size is greater than the number of the features. For example, in this case, we have feature is 2, but we have like more than 20-30 points. So n is greater than sample size. Sample size is greater than the dimension of the design matrix. But there are some cases we have the n is less than d. But when you solve this design matrix, if we have our model to be y equals to x omega, this model has no intercept. So this linear model will always across origin. Okay, but to include the intercept term, okay, we usually use this augmented design matrix. In other words, for example, we always include the 1 as one of the column. So for example, we have the x1, x2, and we include 1 for each individual observation. And we have the w1, w2, and alpha. So this gives us the x1, w1 plus x2, w2 plus alpha. Okay, so by including the 1 term, we can include the intercept terms in our linear model. So in other words, usually we call this design matrix to be the augmented design matrix. So in the following, we just include not only the observation features, xn1, xnd. But also we include the 1 columns in the feature space, in the design matrix. Okay, so in future we will, in the linear regression setting, we will denote this as our design matrix. So this will be a dimension n times d plus 1. And w is a vector w1, wd with intercept alpha. Maybe let me use the red different colors. Okay, so now our linear model will be y equals to x dot product with multiply the w vector. So this is our linear model. With intercept term. Okay. So now the problem simplifies to, we want to find, the goal is to find this w vector that minimize the distance between xw subtract y, because this is a vector, right? This is n times d plus 1, and w is d plus 1 times 1. So this will be a n times 1 vector, right? And the y is also d plus 1 vector. So this is a vector. This is a vector. And for vector, we can find the length of the vector. And our linear regression problem is equivalent to solve the w to minimize this cost function. And this cost function in statistics has a special name called the RSS, given each w. So residual sum squares is called the residual sum squares. Or you may ask, why don't we have this 1 over n in front? Because we are solving the minimization problem. So adding a constant or not adding a constant does not matter. Okay, let's continue. Actually, this some residual squares can be optimized by calculus. Actually, we can rewrite this. If you expand this square, this can be written as W transpose X transpose X W minus 2 times Y transpose X W plus Y transpose Y. Because we are looking for the minimizer. So by calculus, we know the minimizer, you just find the derivatives, right? So here we are finding the gradient for multivariate case with respect to W. So this will equals to, by the way, here we're gonna use one formula. If you have the quadratic forms, X transpose X, a matrix times X, and then you take the derivative with respect to the vector X, you will get 2ax. Okay, so that's the first formula. Second formula is, if you have the matrix multiplies a vector, you take the partial derivatives with x vector, this will equals to matrix A. It's very similar to our calculus problem, univariate calculus, like if you take the derivatives a square x square, right, with respect to x, you get 2ax. So this is just the matrix version of this. Also, you have the constant times x, you take the derivative, you get a constant a. So that's that's the formulas we're gonna use here. So this is a quadratic form, right? This is the w a w. So the derivative will be 2 times x transpose x w, okay, minus 2y transpose x. So if you have the derivative ax, you just have the constant in front, and the last term is just a constant. We get rid of it after derivative, and then we set this equal to 0. We solve for w. Okay, so if you set this equal to 0, we can get x transpose x, w equals to y transpose x. Okay, this has a name called normal equation. So in general, if x transpose x is invertible, then we can find the solution for the w. It's just x transpose x, take the inverse, and y transpose x. So that's the solution for the linear regression. But there are some cases, but if x transpose x, sometimes you find the inverse, trying to find the inverse of this matrix is not invertible. It's because it's singular. Singular means sum of the eigenvalues equal to 0. And so this implies the solution is not unique. Actually, there are a few remarks here. The linear regression, the analytic solution w equals to x transpose x inverse y transpose x. Oh, sorry, I think I made a small mistake here. A small typo here. So when we write down this, a small typo here. I forgot to add the transpose here. So this should be should not be this one, but transpose of this one. Otherwise, the dimension does not match, because this will be a 1 times d. Because this will be 1 times d, but here we have d times 1. The dimension does not match. That's usually where you find the errors for your matrix calculation. So you need to at least match the dimensions. So here is x transpose y. Okay, now this is this is dimension d times n times 1. So this will be d times 1. So the dimension matches, so we can subtract each other. Otherwise, we cannot subtract vectors with different lengths. Okay, good. So now, so therefore here, also we need to change to x transpose y. So here we also need to change to x transpose y. Okay, so same thing here. X transpose y. There is one remark. Actually, everything in front of y, x transpose x, inverse x, is also called the pseudo-inverse. Of x. Okay, so because x is a matrix, not a square matrix, right? X is n by d plus 1 matrix. So how do we define the inverse of a matrix that is not inverse? So this is the pseudo-inverse, which is sometimes denoted by the x plus. This is because if you take the x plus multiply with x, this will equals to, because x plus equals to x transpose x, you take the inverse x and multiply x. Oh, sorry, I mistransform. So this, because this is the inverse of this one, these are now the square matrix. So this equals to in. So this, therefore, this is called the pseudo-inverse of the X matrix. But I think it's not dimension D. This should be dimension D plus 1, identity matrix D plus 1. Okay, so now what's the predicted value of y using linear model? The predicted. Of y. Which we denote with yi hat, which is given by you're using w given inner product with xi. So which is given by x w which is, so let's use xi transpose w, which is equals to xi transpose, and then we have the x transpose x inverse x transpose y, and this is wait a second. Maybe let's use don't use the individual in observation. Let's write down the whole design matrix one. So predict value y hat equals to x design matrix. So this will be n multiply dimension n by d plus 1 matrix, and this is multiplies the w. So w is here, right? So w is here. So this will be x transpose x inverse x transpose times y. So this, if we denote this first part matrix by H, so this is HY. This H is called hat matrix. So anyway, so what this y hat is? Y hat just tells you the value that predicted by this hyperplane. It's our linear regression plane. Okay, so this is our y hat, and this is our y, observed y. So the differences here is residue. Okay, so this is what I plan to cover about linear regression. And the next class, next video, we're gonna talk about logistic regression.